Exactly. So then we should now do this, okay? Artificial science. Use beautiful, attractive, okay? Complex things, okay? But useless. The girl want to put this flower to the glass. Use her mouth. And then stand on 9 lightning bubble. And then this, beautiful, okay? But too complicated. You'll be a scientist. You just take the flower to the glass. Okay? Then you'll find there are many papers published on science, on nature, do this way. Okay? Much difficult. Make simple things complicated. So if you want to do something useful, you must take attention to the interface. This is because interface generates almost all the function. Okay? The key point of interface is to break down the symmetry. Okay? Surface. And as for the interface phenomena, we just focus on one thing, weightability. Okay? This is a summary, today's talk, 18 years work on this field. Okay? Contact angle larger than 150, superhydrophobic. Contact angle be 0, superhydrophilic on the interface, inner surface of channel or surface fiber. Okay? We start from the lotus leaf with contact angle larger than 150. Dirt on its surface can be washed away very easily, and then we find there are many microstructures on the surface and many nanostructures on these microstructures and many nanofibers on the bottom. Okay? And this gives you a hierarchical, okay? Hierarchical structures. Okay? And this surface was coated by the Planck's wax, lower surface image materials. Okay? And then this micro-nano composite surface structures not observed only on lotus leaf, but also on the compound eye of the mosquito, microstructures, nanostructures. Okay? And then interdistance about 100 nanometer. Again, on the leg of a water stratum, it can walking on the water surface. Okay? Microstructures, nanostructures. So something question. Why 100 nanometer, interdistance 100 nanometer? Okay. In 1999, David Chandler did a simulation. So he is want to simulation of the protein assembly. The driving force of protein assembly is hydrophobic stress. So what he wants to know is that the critical distance between the two hydrophobic solids, and then where the water cannot enter space between. Okay, he used this equation. And then the simulation at room temperature, normal atmosphere, give you 1,100 angstrom. It means two hydrophobic solids close to 110 nanometer, the water surrounding cannot enter space between. So this is the side effect of the lotus. And then human beings only understand this by the end of last century. And then nature already know it millions of years ago. Okay? And then after this, we understand we use very polymer, hydrophobic polymer, amphiphilic polymer, make these nanostructures superhydrophobic, very cheap materials, and make it. And many polymer scientists join in this field. You will see this field grew very fast. See, last year, okay, around 1,800 publications come all over the world. Okay, last year, okay, 87 countries and 40 university institutes join in this field, including Harvard with MIT, and also some university in UK, University of Tokyo, so many, and Hong Kong also. And then this field, a ranking by Global Research Report of Science, Material Science, be number 7. Okay, you will see who are in front of us, and then this high TC is behind us. Okay, and the first law. First law we get from nature is that the cooperative effect of the macro nanostructure and surface energy are the key of superhabitability. The first law. Software also find anisotropic superhabitability. Okay, even on the leaf, rice leaf, okay, the arrangement give you anisotropic effect. Okay, the water droplet is easily rolling along this direction, difficult in the perpendicular directions. And then give you this arrangement. Arrangement can make the anisotropic effect super hydrophobic. And again, on the wing of the butterfly, so the water droplet can only rolling outside, cannot difficult rolling inside. Directional, okay, rolling behavior. Okay, this has strong relationship with the orientation of this microstructure and this nanostructure. Orientation control. Okay? The second law. The arrangement and orientation of micro nanostructure may control the weighting state and motion tendency of liquid. Okay? And after, let's try to do some chemistry. Okay, and let's dissolve those Planck's wax from the lotus leaf, and then the surface changing from superhydrophobic to the superhydrophilic. Okay, superhydrophilic. It means water angle will spreading completely to the zero. Okay, and then we tried many polymer, many kind of PDMS and PVA. Okay, and then we find something here. Okay, 65, around 65 degree. So yeah, above 65, see, enhance makes it more hydrophobic, and then lower than 65, so enhance to more hydrophilic. So what does this mean? And so the third law is that the macro nanostructure enhancement effect on both hydrophilic and hydrophobic. And then what is the physical chemistry meaning of the 65? Okay, so a threshold value for the roughness enhancement to the weightability. The meaning that also again by the end of last century, Viola, he collected 17 years of data of water adhesion tension of water to the different kind of subject. And then he tried to give a limitation between attraction or repulsion force of the water molecule to the solid by attraction or repulsion force. And then this water adhesion limitation just corresponding to the normal water content angle be 65. This means what you learned from the textbook, 90 degree, is the limitation of the hydrophilic was wrong. Okay? Then that's because this just you get this angle by cosine theta equals 0. Cosine theta has nothing with physical chemistry. Okay? It's just the equation of the mathematics. Okay? So if you understand this, you can try many liquids. Okay? Many liquids have its threshold volume. Okay? And that has nothing to do with 90 degree. Okay? And this table should rewrite on the textbook. Okay? So after you understand this, so why not we select the polymer who can change their weightability? So above or below 65. Okay, then we can get super hydrophilic switching. And then polynippon is a famous polymer. It's temperature driven system. And then we realize this, that it was 2004. Okay? And then the editor offered us a cover. And then we draw this yin and yang, Taiji symbol, onto the cover. But we are really hesitant about this that time. But the Japanese editor understands this. Okay, the editor, I don't know he or she. Okay, the editor, right? The yin and the yang represent the two operating fundamental properties of nature and the universe in ancient Taiji Chinese philosophy. Okay, Chinese philosophy. It's very important. We learn a lot of from the West, the way of to the research, but we should not forget ancient Chinese philosophy. It's very important. This composition will make you much smarter. Okay, let's go.